Hey, AP Chem. We're in the middle of a discussion about molecular orbitals, and there's really one more concept we need to add to this idea. And that's the idea of where the electrons actually are when orbitals overlap and form a bond. So, this theory of molecular orbitals is pretty complicated, right? We started talking about how the idea of a molecule, both the bond length and the angles which happen inside a molecule, can't be fully explained through atomic orbitals, right? Atomic orbitals overlapping is going to lead to different bond lengths and different bond angles than we actually observe in molecules. And so what we assume is that when atomic orbitals overlap to form molecules, the orbitals actually hybridize and we get a couple new things out. So first of all, the orbitals change shape. So molecular orbitals are a different shape than atomic orbitals. Second of all, the orbitals change angles. So molecular orbitals are at different angles to each other than atomic orbitals are. We also talked about how that overlap of molecular orbitals can lead to different types of bonds. Direct head-to-head overlap is going to lead to a sigma bond. Sideways overlap is going to lead to a pi bond. Okay, so we talked about how molecular orbitals hybridize. We talked about how the different types of bonds that can form when they overlap. So this is really the third concept in this whole overarching view of molecular orbitals, and that's where the electrons are. When that overlap occurs, the electrons aren't just in the cloud anymore. The electrons are actually localized in certain areas of the orbitals, and that's what we're going to talk about today. That's kind of our last concept here. So we're still talking about the same thing. This is not a new concept. It's just the third piece to this concept. Okay, so let's talk about it. Now, when we talk about where these electrons are, again, we're going to go back to a really simplified view of molecules. So we're not going to deal with really complicated molecules within this theory. In order to explain this theory, we're going to go back to some of the simplest molecules we can talk about, and those are the diatomic molecules. So we'll start by talking about hydrogen, and then diatomic helium, and then lithium, and then beryllium. But we're going to stay with monatomic or mon-elemental diatomic molecules for this discussion. Also, we're going to go back to talking about the simplified molecules, and therefore we're going to use some simplified orbitals as well. So for hydrogen, for example, the two orbitals that are operating when we're dealing with a hydrogen bonding with another hydrogen is the 1s orbital, right? Because hydrogen's one electron exists in the 1s orbital. Okay, so you may be saying to me here, hold up, Martins. I thought you just told me that this was an extension of the molecular orbitals that we're talking about, and 1s is not a hybridized orbital. That's true, right? Okay, but this would also work for the hybridized orbitals that we're talking about. So we're just trying to deal with the simplest possible setup in order to discuss where the electrons are. And that's why we're not going to be talking about like sp, sp2, sp3. We're going to go back to the simple stuff from hydrogen, and hydrogen doesn't hybridize its orbitals because it doesn't need to, right? So we're going to talk about the 1s orbitals for hydrogen again. Okay, still an extension, still part 3 of this whole molecular orbital idea. All right, so when hydrogen overlaps, that 1s overlap. So here you can see a little chart down here at the bottom. Notice that we have atomic orbitals for each of our bonding atoms. So we're going to, in this case, we're going to have hydrogen bonding with hydrogen. So we're going to deal with each of the atomic orbitals for hydrogen, which is a 1s, each of the atomic orbitals for hydrogen, which is the 1s. Now, when the atomic orbitals overlap, I'll draw that on this side. Okay, the 1s orbitals get close enough to have a little overlap. They overlap here in the middle. Okay, so we have a nucleus for hydrogen somewhere in the middle. We have our electrons in our cloud. Our clouds are overlapping. And the happiest place for those electrons, we already talked about, is right in the plane of the nucleus, right? Above and below, like the p orbital overlap that leads to the pi bond. It can lead to a stable bond, but it's not the most stable place. It's not the lowest energy place for the electron. The lowest energy place is going to be in the plane of the nucleus, overlapping right in the middle of the nucleus. However, notice that the 1s orbitals, how many electrons can the 1s orbital hold total? Well, the 1s orbital is like any other orbital that can hold 2 electrons. So the 1s orbital can technically hold 2 electrons. And we've talked about before how those 2 electrons really, any one orbital can really only hold 2 electrons. So this little space in between the hydrogen, when we draw hydrogen as a Lewis structure, we draw it as if it has the 2 electrons in the middle, right? So we have 2 electrons in the middle. But what if you had a third electron? What if you had, instead of having H2 as a molecule, what if you had H2 minus as a molecule? What if we had a third electron? Where would that third electron go? Only 2 electrons really can fit in between these 2 atoms, in between the nuclei in that orbital. And so if we have more electrons, they can't go in the middle like that. They have to go someplace else. And the place that they go is actually on the outside. So if we return, let me just clear this real fast. Simplify our view here. So if we have 2 hydrogen nuclei, right, we are trying to represent H2H bonded to H, right? And we have 2 electrons that are going to exist in this region. 1, 2 electrons. If we had a third electron, so we're talking about H2 minus here, that third electron couldn't fit in between the nuclei. It would have to go outside the nuclei. And so what we start to see here is we start to see electrons that are very stable, electrons that are in a very low energy state. Those would be the ones in the middle, and we call those bonding electrons or bonding orbitals. Okay, and if we have more electrons that we have to accommodate, they're going to go outside the nuclei into this very unstable area, this very high energy area. And so what we're going to call those areas are antibonding. Antibonding orbitals. Okay, so here is something that we see when atomic orbitals overlap into molecular orbitals, and they hybridize into molecular orbitals. Okay, what we get are these areas where the electrons exist in the molecule. And the areas where electrons exist in the molecule really get split into 2 separate orbitals. The bonding orbital that can hold 2 electrons and the antibonding orbital that can hold 2 electrons. So notice the bonding orbital is at a very low energy state. It's actually lower than the atomic orbitals were separately. When hydrogen is an atom and it's holding 1 electron, when those orbitals overlap, it forms this area in between 2 nuclei where the electrons are even more stable They're even more stable in between the two nuclei than they are attached to one of the nuclei by themselves. But if we get a third electron and it gets forced outside of those two nuclei, it's going to be extremely unstable. And that's where we see this higher energy antibonding orbital. And so we have two atomic orbitals, okay, 1s and 1s. We're going to get two molecular orbitals out, just like we've seen so far. And we're going to call these 1s, the 1s orbital, which is our bonding orbital. And we're going to call the high energy one 1s star, which is our 1s antibonding orbital that represents the space outside of the two nuclei. Okay, so this idea that there are certain spaces where the electrons can exist in between the two nuclei, outside of the two nuclei, lower energy states, higher energy states, bonding, antibonding orbitals. This leads us to an explanation and a prediction about which bonds will form and which bonds won't form. So watch this. Okay, if we're talking about hydrogen, diatomic hydrogen, right? It comes from H and H. Those are our two atoms. They combine to form H2. That is our molecule. So each of the hydrogens by themselves carry one electron. So when we combine those two together to form H2, which is our molecule, we're going to have two electrons that both fit inside our bonding orbital, right? And we're happy. It's a happy bond. H2 is a very stable molecular structure. And it looks like that when we look at this energy diagram, right? We take these two electrons that are at a higher energy, we combine them, and now they exist at a lower energy. They're more stable. Let's look at this same system for He2, for diatomic helium. Let's look at a similar situation. Okay, so diatomic helium, each atom of helium is going to have two electrons, right? So when we combine those two atoms into a molecule, diatomic helium, we have four electrons we have to deal with. So the first two are going to exist in between the nuclei. So here's our 2 plus nuclei, right? These two electrons are going to exist in between the two nuclei. Well, the next two electrons, because we have four total, right, are going to be forced outside of the nuclei. I'm going to box those so you can see the difference. Okay, they're forced outside the nuclei. This is a very high energy system. This is not a very stable system. And so what we get are two that are very stable and two that are not stable at all. And we can describe this system with something called a bond order. And what a bond order does is it takes this energy diagram and translates it into a numerical prediction. So what you do for bond order is you take half of bonding minus antibonding electrons. So in this case, I have two bonding, I have two antibonding, two electrons in the bonding orbital, two electrons in the antibonding orbital. So 2 minus 2 is 0 times a half is 0. So my bond order for He2 is 0. It is essentially predicting no bond. He2 is unlikely to form a bond because it has no advantage to form that bond over the atoms compared with hydrogen, right? Remember that diatomic hydrogen resulted in two electrons in the bonding orbital and no electrons in the antibonding orbital. So the bond order for hydrogen is going to be 1/2 of 2 minus 0, 2 electrons in the bonding orbital, no electrons in the antibonding orbital. So our bond order for hydrogen, diatomic hydrogen, comes out to be 1, which is a prediction that a single bond is going to form for diatomic hydrogen, which is what we see. We see a single bond form for diatomic hydrogen. We don't see any bond form for diatomic helium. And so we see this theory of where the electrons, the areas where the electrons get forced into in this localized electron model, serves as a predictor as to which bonds will form and which bonds will not form. All right, deep breath. At this point in time, you should be able to describe to me where the electrons go when molecular orbitals overlap. When orbitals overlap to form a molecule, you should be able to describe to me where the electrons get forced relative to the nucleus and how that leads to stable versus unstable systems, and how we can actually describe those systems numerically using a bond order, which helps us to predict the bonds that occur or don't. Okay, so that's where we're at so far. We're going to do this again for a couple more atoms, a couple more molecules, and see where that leads us. So here is that equation that I just talked about to calculate bond order. 1/2 of all the bonding electrons minus all the bonding electrons. So it's bonding minus antibonding times 1/2. All right, so let's do this for lithium and beryllium. All right, so lithium and beryllium. Oh, I don't know why I drew 4. All right, here's lithium. Here's lithium. So atomic lithium is going to have 3 electrons, right? So we have the 1s, which holds 2 electrons, and then we have a 2s that holds 1 electron. Okay, so when these combine, the 1s orbitals are going to overlap, and they're going to form a bonding region and an antibonding region. Okay, so this is 1s bonding, this is 1s antibonding. Okay, the 2s orbitals are also going to overlap and form bonding and antibonding areas. So here's your bonding area for the 2s, and here's your antibonding area for the 2s. Okay, so now we need to look at, so molecularly, as a molecule, diatomic lithium, where do these electrons fall? Let's do them in pink, shall we? Okay, so I have 1, 2, 3, 4, 5, 6 electrons to deal with. So 1, 2, 3, 4, 5, 6. Okay, so here's where the electrons fall for diatomic lithium. Let's look at bond orders at this point in time. So if we just calculate a bond order from what we have right now, we're going to go 1/2 all our bonding. So we have 1, 2, 3, 4 in the bonding orbitals, and we have 2 in our antibonding orbitals. So we have 1/2 of 2, which is 1. So for a diatomic lithium, we would predict that this molecule would occur and it would have a single bond. Now, a couple things to notice off of this. First of all, look at the core electrons. Okay, so the core electrons are below this line. If we were to consider a bond order for just the core electrons, it would look like 1/2, 2 minus 2, which is 0. So notice that the core electrons really don't contribute much of anything at all to the bond order. It's a wash. The core electrons provide a wash. And so we've talked about before how only valence electrons are involved in bonding. Well, this is why, or this is a model that can explain that for us. because the core electrons, if they were to overlap, some of them would be forced into a lower energy system, some of them would be forced into a higher energy system, which provides really no advantage to the molecule at all. It's kind of a wash. Only the valence electrons really contribute to the bond order. If we were to calculate a bond order ignoring the core electrons and only using valence electrons, what would we get? 1/2 2 minus 2, 2 minus 0, because there's no electrons in that antibonding orbital, which is 1. So notice that the bond order of us only looking at the valence electrons is the same as the bond order for us considering the valence and core electrons together. So core electrons really add nothing to bonding. We really can just look at valence electrons in order to understand the theory of bonding. Okay, let's do the same thing for beryllium. Why don't you pause the video here and try beryllium by yourself? Would you assume that beryllium is going to form a diatomic bond? And if so, what kind of bond would it form? Okay, so I'm going to write out the atomic orbitals for beryllium. You don't have to do this, but I do want to show you where this information comes from. So beryllium has 4. 1, 2, 3, 4. 1, 2, 3, 4. So if we look at diatomic beryllium as a molecule, we'll have bonding and antibonding for 1s. We'll have bonding and antibonding for 2s. And we fill it in with all 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so our bond order, I'm just going to consider the valence electrons above the line. You can do that also, or you can do it with all core and valence electrons. So 1/2 bonding minus antibonding equals 0. So I would not predict a bond. I would not predict that diatomic beryllium would exist because the bond order is 0. It's a wash with the core electrons. It's a wash with the valence electrons. There's no advantage for beryllium to form a diatomic molecule. Okay, let's look at boron through neon. So when we cross over the line from the s orbitals into the p orbitals, we also see the same overlap with the p orbitals. Now, this diagram is starting to look kind of crazy. Notice a couple things. First of all, I'm ignoring core electrons. Since the 1s overlap ultimately turns into a wash anyway, I'm going to ignore it. Second of all, notice that the p overlap, the bonding and antibonding areas, or the bonding and antibonding orbitals that occur when you get the p overlap, are a little bit more complicated than when you get the s overlap. So let's break this down. Notice I have 2p sigma and 2p pi bonding. I also have pi antibonding and sigma antibonding. Also notice that there's 1 sigma and 2 pi for bonding. Same thing with antibonding, 1 sigma, 2 pi. So where does this come from? Well, let's look at the overlap that occurs. So if I'm looking at the 2p orbital and the overlap that occurs from it, here's 2px, right? Here's 2py, and then 2pz is coming out at you in the plane and going back into the plane. So I'm going to try to draw it here like a diagonal. Okay, so I have x, y, and z orbitals for my 2. Now let's draw this. We're going to have a second molecule. So for beryllium, for example, we have a 1s overlap, we have a 2s overlap, we have a 2p overlap, and we're going to have a 2px is going to overlap, and that is going to be a head-to-head overlap. So what kind of bond is that going to lead to? That's going to lead us to a sigma bond. So that would represent this little box right here. The 2p sigma overlap is a direct overlap. Okay, I'm also going to have a 2py. All right, so I have a Y for my beryllium, and they're going to overlap side to side. Now, I drew them kind of far apart, but you can imagine the overlap that occurs side to side, side to side. And so that overlap is going to be a pi overlap. So notice that's going to be one of these boxes here, my pi overlap. Now, where does I have my sigma overlap. My sigma antibonding is going to be way the heck out here on these ends. So notice it's really far away from the nucleus. And that's why it is the highest energy antibonding orbital of this whole system. So the sigma overlap can be the lowest energy orbital for the bonding orbitals, but it can also be the highest energy orbital for those anti-bonding orbitals. The pi overlap, we have the overlap that's directly above and below the nuclei. That leads us to our pi bonding. Now, our anti-bonding is just going to be on the other side. So it's really not that drastically different than the pi bonding. It's a little bit different, right? If we look at this overlap separately, right? We actually bring them close enough to see a real overlap here. We can see that my nuclei are here. My bonding is going to occur here, which is above the nucleus, but still between them. My antibonding is going to occur here, which is above the nucleus, but outside of them. So it is a little higher energy. It's still an antibonding orbital here. But it's not quite as drastically different as that sigma overlap. And then we have the same thing for the x-axis. So the x-axis are coming out, going towards you, right? Like this. They're going to overlap this way. You'll have the bonding in between them. You'll have the anti-bonding on the outside. So I'll draw my other x orbital there. Okay, and then we're going to have bonding happening again in that area there, which is going to lead us to a pi bond, since it's a head-to-head, or it's a side-to-side overlap, right? And then on the outside of those overlaps are going to be your anti-bonding. So we'll get this right here is going to be our anti-bonding. This right here is going to be our bonding. So it's a little bit more complicated than the SS overlap, because we have different types of overlap. We have a head-to-head for the 2px, and then the 2py and 2pz are going to be side-to-side overlap. So that's why it comes out to be a little bit more complicated. But then it fills the exact same way. So if I am going to look at diatomic beryllium, for example. Okay, so beryllium has 5 electrons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so I'm going to take those and fill them in. So I have 10 electrons to fill in. I have 1, 2, 3, 4, 5, 6, 7, 8. Notice, just like in atomic orbitals, if you have a degenerate orbital, you have two or three orbitals that are the same energy. The electrons will spread out while they can. They're going to spread out, but then they'll pair before going up to a higher energy level. So that's Hund's rule. For atomic orbitals, still applies for molecular orbitals. So we have 8, 9, and 10. Now, below this line is going to be a wash for bond orbitals. So we'll just look at the bond order above this line, which is going to be 1/2 of 1, 2, 3, 4, 5, 6 minus 0 in the antibonding. It's going to lead us to a bond order of 3. So we would expect diatomic boron to form a triple bond. Pretty cool, eh? And that's the same for boron all the way through neon. They're all going to do the same thing like that. So one of the cool things that looking at these molecular orbitals, the bonding areas, the anti-bonding areas, the bond orbitals can do is it can help us predict what kind of bonds form for these different elements. It can also help us predict magnetism, which we'll talk about in just a second. Now, there is kind of a catch here, and that is, okay, so on this diagram, I have built molecular orbitals for diatomic boron through diatomic neon. So if you look at this, okay, so notice this is only for the valence stuff. So below this line is 2s. So this is my 2s bonding. This is my 2s antibonding. Above this line is 2p. So I have my 2p sigma, my pi 2p, my pi 2p antibonding, and my sigma 2p antibonding. Okay, so notice that it's just dealing with valence electrons. It's not dealing with core electrons. You'll notice something else. What else do you notice about this chart? Notice that boron, carbon, and neon have their sigma and their pi's flipped. Remember, anytime we try to describe what we're seeing in nature through a model, our model is going to break down at the extremes, right? It almost always does. And this is no different. And so when our model breaks down, we have to make accommodations in order to change our model to describe what we're actually seeing in nature. Otherwise, our model isn't very useful, is it? So what we notice, especially when it comes to magnetism, is that boron, carbon, nitrogen, their sigma bonding and their pi bonding is actually flipped in energy. And so when we fill these out, that makes a difference. The sigma and the pi antibonding being flipped actually makes a difference, especially when it comes to magnetism. So let's talk about magnetism just a little bit. Okay, so as we fill this out, what we see are when we are left in this diagram with an unpaired electron, unpaired electrons, it leads to an attraction to a magnetic field. So unpaired electrons lead to attraction to a magnetic field. And there is a term for that. It's called paramagnetic. So something that has unpaired electrons in these molecular orbital diagrams is going to show an attraction to a magnetic field, and that's called paramagnetism. So let's fill this chart out, and then we can talk about which things we would expect to be magnetic based on this chart and which things we would not. All right, so boron we said was going to have 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Carbon is going to have 12. Let's pull up a periodic table real fast so you can follow along. So boron has 5 valence, which will, in the molecule, will give us 10 valence electrons total. Carbon has 6 and 6. Actually, boron has 1, 2, 3 valence electrons. Carbon's going to have 4 valence electrons. Okay. All right, so I have to fix that if we're going to just deal with valence electrons. All right, 1, 2, 3, 4, 5, 6. So carbon has 4 valence, which leads us to 8. 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen has 5 valence electrons. 5 plus 5 is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Fluorine has 7 and 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And neon has 8 and 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so we have our chart filled out. We can do a couple things with this chart. First of all, we can calculate bond orders. What if we have diatomic molecules? What kind of bonds do we expect out of those? And if you were to calculate bond orders for nitrogen, oxygen, and fluorine, you should be able to predict the 3 types of bonds that form from these. Same thing with neon. These are really common molecules, right? Diatomic nitrogen, most common gas in our atmosphere. Diatomic oxygen, second most common gas in our atmosphere. Diatomic fluorine, very common, very dangerous, very secured, not easily bought at the store or floating around our atmosphere, but it is a common molecule. And then neon, is diatomic neon common? No, it's not. Atomic neon is really common. I would hope that you guys can predict the bond order for that one off the top of your head. So this would be a good time to pause the video and calculate bond orders for especially those 4 and just see, do they match up with the Lewis dot diagram that you can draw for them? The other thing we can do with this diagram is we can predict magnetism. So if you look through here, which ones are left with unpaired electrons in their diagram? Well, diatomic boron has unpaired electrons in the diagram right there. And then also oxygen is left with unpaired electrons in the diagram right there. All of the other ones are left with paired electrons. And this is one of the reasons why flipping those sigma and pi is a must, because if those sigma and pi weren't flipped, then you would get different predictors of magnetism based on this chart. So it's important to flip those. Now, you do need to be able to talk about bonding and antibonding orbitals and calculate bond order off of different things, but you would not be expected to be able to draw this chart and know which ones have the sigma and the pi flipped. If you ever needed to use this chart, they would have to provide it for you. So you should be able to function through the chart, but not come up with the chart on your own. Okay, so let's talk about oxygen for a little bit. I'm going to delete this and move forward. Okay, so here we see the definition. In the presence of a magnetic field, 2 types of magnetism can be induced, paramagnetism and diamagnetism. And then, like I said before, paramagnetism is going to be associated with unpaired electrons, and it leads to an attraction into a magnetic field. Anything that has all paired electrons in this chart, we call that diamagnetism, and it actually gets repelled out of a magnetic field. So unpaired electrons are attracted into a magnetic field, paired electrons repelled out of a magnetic field. Paramagnetism is attracted into a magnetic field. Diamagnetism is repelled out of a magnetic field. Okay, and actually, so anytime they explain this to you, the whole like attraction into or repulsion out of, they use this little scale thingy. And so if something is attracted into a magnetic field or paramagnetic, the scale will be tipped like this, so the thing gets pulled into the field. If it is repelled out, the actual sample here is going to be pushed out of the field and the scale will tip this way. So I don't know if they, if this is like the official test or whatever, but for whatever reason, anytime you see this discussion, they base the discussion off of this scale. So for what it's worth. Now, the coolest part of this, I think, is actually seeing magnetic oxygen. So there's a little demo that a college professor does. I want to play that for you quickly. So you can actually see oxygen being magnetic.
I made this morning in my lab. Some cracks on it, and they're all due to me, but we're about to, we're about to do it again. Okay. So this is a nice big magnet. Zoom in here, try and get some light on the subject. I think that's relatively clear. We got some shadows here, but there we go. Okay, so heat big magnet. If you put a piece, it took me half an hour to get the bar that was stuck in here this morning out of there. Let's try some liquid nitrogen. Now, the reason that I brought liquid nitrogen is obviously there's lots of nitrogen in here now because the air is 80% nitrogen, but you can't see what's going on. So let's condense the nitrogen, and when you condense nitrogen, you get liquid nitrogen. Looks like water, but it's at its boiling point. It's at minus 192 degrees C. Okay, it's cold stuff. You've got to chill down the air to minus 192 before this stuff condenses into a liquid. You don't have to worry about it. You're already breathing. I have to finish that sentence. You're already breathing nitrogen. You will continue to breathe. Now, if we go back and look at the, let's do that, MO diagram of nitrogen. Where do we have an NO diagram of nitrogen? I don't remember. It's going to be way back there. There's nitrogen. No unpaired electrons. So I would predict that this stuff is not paramagnetic. Let's see if it's true. It should not stick to the poles of a magnet. Now simply pour this into the magnet. Whew. A little chilly when it goes down your pants, I'll tell you. It's okay, no, don't worry. Nothing happens. It doesn't stick to a magnet. There's no unpaired electrons in it. That cracking sound is the camera, but I'm not going to worry about that. Now we have liquid oxygen. So, whoops, I made this by putting a copper tube inside a flask and filling up the flask with liquid nitrogen, and then blowing oxygen through the tube. Oxygen's got a higher boiling point than nitrogen. So you can condense gas phase oxygen into liquid oxygen by pushing it through liquid nitrogen. And I'll just put some in a beaker here so you can see it. It's got a lovely blue color. I'm hoping you can see that color. Okay. It's blue because of the electronic transitions that are going on in here. It's actually a very complex process, but it's one photon exciting two electrons at the same time. And the absorption of radiation is in the red and yellow and green portions of the spectrum, and that leaves the blue for you to see. It's absorbing everything else. So it's liquid oxygen. It's the same stuff you're breathing. I mean, it's not going to hurt me to do this or anything. It's perfectly normal. But let's pour this through the magnet and see what happens. Isn't that just the coolest demo in the world? I love this demo. It sticks to a magnet. Oxygen is magnetic. It's paramagnetic. It's not your everyday experience. Why would you think it would be? Well, you only see this, of course, because the oxygen is so dense here. It's about 4,000 times as dense as the oxygen in the atmosphere. Let's do that again. As in the atmosphere. So you can only see it when it's a liquid, but it actually sticks in the poles of a magnet. This stuff is so much fun. I actually meant to bring something else because there's lots of things you can do with liquid oxygen. but I forgot to bring something. So unless anybody has some steel wool in their pocket. Some people are actually checking. You carry steel wool often? No? Okay. Okay. But I'll do that when we get to kinetics. There's a good reason for doing that too.
Okay, so there you go. Oxygen is paramagnetic. And that's it. So that's the whole theory of bonding as far as we're going to talk about it. That's chapter 9. I know it's a little bit crazy. We'll do some practice with that in class. Definitely bring your questions. Give yourself a day or two to process through this information. We'll deal with your questions, and I will see you in class.